So we are back to our transistor tester circuit again, and I have added the diode and changed the resistors, so let's try to measure the voltages. And I am still measuring this to the ground point, so not to the negative supply, but to the other side of the diode. So the voltages on the paper should still be correct. And we have the high voltage here. That should be for the low gain. That is measuring 3.3 volts, so let's just measure the supply rail. That's 3.312, so that's a 12 millivolt drop, and that's exactly what we got on the paper as well. So that should be fine. Let's measure the lower voltage, or the high gain cutoff. And that is 1.06 volts, so that's close enough to the 1.05 that we calculated. So let's just make a test to see if we have any problems down at the lower end on this comparator when we get down to below 1 volt. So let's put a transistor in there. So the transistor is connected correctly and the LED comes on. And if we connect this the wrong way around, so we connect the base to the test resistor so we can short this to ground, well, the LED just comes on for a split second there, but it stays off, so that shouldn't be a problem. And let's just measure the voltage here, and that is 0.8 volts, so at least it seems to work with the transistor. But let's try to put a jumper wire in instead, so we are shorting it directly to ground. And the LED is still off, so that should be fine. And we got 28 millivolts there, so it is indeed shorted out. But there still is some bad contacts in this breadboard, because this current here should of course be 33 milliamps, because we are dropping 3.3 volts over this 100 ohm resistor. But we are not dropping 3.3 volts, we are only dropping 2.9 volts, so there must be another 0.4, 0.3 volt drop in the contacts in these wires. But I think we can still have quite good confidence that this is going to work now. And as I said, I am going to power this from a 9 volt battery, so it could be nice to have some kind of indication whether or not this battery is actually still functional. So we will need at least 5 or 6 volts for this circuit to work, and the 9 volt battery is already dead when it gets down to 5 or 6 volts anyway, so we have a bit of a margin to put in some circuitry to measure this voltage, to give us a warning when the battery is low. And as it turns out, we actually already have all we need to build a circuit that can detect the voltage, because we're using a TL074 opamp, and we're only using 2 of the opamps in this. This is a quad opamp, and we will actually only need 1 opamp to do this, because we already have a 3.3 volt regulator in there, and we can use that as a voltage reference and divide this voltage down and compare it to the voltage reference. So that can tell us when this, if we for example divide this by 2, then it will be 4.5 volts when it's good, and when this drops below 6.6 volts it will get below the voltage reference, and the comparator will turn on or off depending on which input you have connected it to. So we could do something like that. But I think 6.6 volts is a bit low, so we'll set it a bit higher to about 7 or 7.5 volts. I think for a 9 volt alkaline battery that is dead at about 7 volts, if I remember correctly. And if it's not an alkaline, I think it's even worse than that. So I have finished up the rest of the circuit here, and I chose a cutoff voltage of 7.26 volts. Because that will let us choose some resistor values that does actually exist. The battery voltage gets divided down. The 12K is connected to the battery, and the 10K to, actually not to ground, but to the negative terminal. I should correct that. Of the battery. When this voltage hits 7.26 volts, that will be equal to 3.3 volts. So anything below this will turn off this LED, or turn off the output. And the LED is connected to a resistor to limit the current. And I've added a diode in series. I don't think I need that, because after we added the diode to the supply voltage, this will only go down to 0.7 volts. Remember, when we first tested it, the low voltage was 1.4 volts. And that could actually still light up this diode, so that's why I added it. But now that we're still connecting this to ground, that will only be 0.7 volts, because that is 0.6 volts higher than the negative terminal. And the negative terminal is connected to the opamp. So that's a little confusing, but I will add it anyway. So just to be on the safe side, it will not do any harm, at least. So now we should be able to see if our battery is good. If this LED is not on, it means we need to change the battery. So we just have to test it to see that it works, and the comparator doesn't do funny things when this drops way too low, because if this one drops so low that our regulator cannot regulate, the voltages might be the same, and who knows if this will be on or off, so we'll have to test that. I don't know if the comparator can actually work at 3.3 volts, so when this is dropped all the way down. But we can do a test to see if it works, and we'll do that. So I have connected everything from the schematic we just drew to our transistor tester circuit, and we have the LED here. And I am measuring the supply voltage with the multimeter. So let's try to turn on the power. And the LED comes on, so that should be a good thing. Let's try to turn it down a bit and see when it, oops, it already cut out there. What this, oh, I think I know why. Because this voltage here, the comparator will actually not see that as 3.3 volts, because as I said, I added this diode on the negative supply rail, so that will actually be 3.9 volts or thereabouts that the comparator will see. So we'll just have to measure that and change one of these resistors. I think that's what's causing the problem, but we can just measure that. So here is the inverting input, and that is supposed to be the reference for the comparator. And that is the non-inverting, so that's the battery voltage that's been divided down. So let's make the calculations with 4 volts instead and see what resistor value we have to use. And this is actually also a reason why it's a bad idea to use a diode on the negative rail here, because it all just gets confusing. And I know I shouldn't do it, but I think it is the cheapest way to get this to work. So I just did the calculations, and it turns out that a 15K resistor instead of the 10K will do the job, so we'll just change that. So that should be better. And let's try to turn on the supply. So the LED is still on. That's the first good sign. Let's try to turn down the voltage. At least it's better this time. So. And we're aiming for about 7.2 volts. Oops. Yeah, that's not bad. That is actually exactly 7.2 or 7.21 or 2 volts. But within 20 millivolts, that's better than I have hoped for, but of course these resistors are 5%, so we might just be lucky. But let's try to turn it down even further, because we don't want it to light back up again. So far so good. Nothing yet. And yeah, now we are below the voltage drop of the LED, so now it won't turn on, that's for sure. And let's just try to rise it slowly back up again. And there it comes, back to life. And again, that's at 7.2 volts. So I'm quite happy with that. So now there is just one thing left to do. I'll give this a decent test and try a few different transistors with high gain and low gain and every possible combination and test that it indeed works. And I will put it on a PCB and I'll test it again to see that these bad contacts doesn't have any influence on the circuit. And I will come back with the finished board, and of course if there's any problem I'll just turn on the camera and tell what I'm changing. So I have made a little PCB for it, but I already noticed one mistake, but it turns out that it is actually not that bad anyway. This node here that I originally connected to ground here, but chose to connect to the negative terminal, I ended up connecting that to ground on the PCB as well by mistake. So these values are a bit out now, but as it turns out, by using two 12K resistors it gives almost exactly the same value, so that could actually be a good thing. So now instead of having to use a 10K and a 12K, people can just buy two 12Ks or a couple of 12K resistors. And I have tested it on the breadboard with this connected to ground and it works exactly the same, so no problem there. So I got the board finished up. I didn't find any major mistakes. I got a self-screen label back to front here, but I'll of course correct that before I upload it to my website. So I added a trim pot to the current source here. So instead of putting the 6.8K resistor in there, I have put a 5.6K in with a potentiometer in series so I can calibrate the current source. But it is of course still an option just to put the 6.8K in there and just put a jumper link across the terminals of the pot. So let's connect this up and see if it works, and then calibrate it and test a few transistors. So our red LED comes on, that's a good sign. Let's try to drop down the voltage and see when it cuts off. Should be around 7.2 volts. Well, that starts at 7.3, so yeah, that's good enough. 7.25. Let's drop it down a little bit further. Let's see if it stays off. It should. Oh, think I saw something there. Yeah, so at 3.33 volts there's just a tiny glow in there. I don't know if you can see that. I'm going to try to turn off the lights. But it is nothing really, you can just see it with the lights turned off. Well, I did also change this to a red LED, so that could actually be the reason, because there's slightly less voltage drop across this one. So let's get this calibrated. So the way I'm going to calibrate this is to measure the current that is flowing out of the base terminal and through the transistor back into the emitter terminal. But in this case I don't have a transistor in there. I'm using the EEV block microcurrent to measure what should be 10 microamps. This can output 1 millivolt per microamp, so that should be 10 millivolts on the multimeter. You could of course just use the multimeter, but I think this is a little more precise. Or I could use my flute, but yeah. And we get 7 millivolts, so that's a fair bit off, but I expected that because I put the pot in here and a lower resistor, a lower value resistor. But we should be able to get this to 10 millivolts. Oops. Gotta get it precise. So that should be about it. So if you don't already know this microcurrent, it's actually a very handy tool. It is not really designed for just measuring current like this. Of course it can do it, but the benefit with this one is it takes away the voltage drop that is normally inside a multimeter. If you draw, say, 300 milliamps on a low voltage microcontroller or something like that, a regular multimeter can actually drop the voltage quite a bit. So if you use this, it solves the problem. But in this case we don't care about the voltage drop at all. We just need to be able to pull 10 microamps out of the current source. So let's try to see if this can do what it was designed for. So let's test some transistors. I'm measuring the input voltage with this multimeter, and I'm measuring the voltage across our test resistor in there, so this should show up as gain. So if you read the millivolts reading, this should give you the gain. So I have a standard NPN transistor here, and let's try to put that in. I have set the switch to NPN, and I'm going to put it in the correct way round. Oops, there's a loose connection in there. I'm not going to use this connector for the finished product. I plan to build a case for it and have some other sort of connector. But as we can see here, it says it has a gain of 338, and that could be possible. So let's try to turn down this input voltage a bit, and this shouldn't change that much if we do. And it doesn't. Let's just drop it down. It changes a few millivolts, but let's drop it down until the red LED goes out. There. So that means our battery is low. Let's take it down a bit further. See when it does misread. It's starting, and it's getting worse and worse and worse, and we're way out. And if we compare that to one of these cheap multimeters with a built-in transistor tester, this is saying 345, and I have no idea about the accuracy of this one, but it does seem promising. I mean, there can't really be anything wrong with this, because when we know we get 10 microamps into a transistor, and we know we're measuring across 100 ohms, that there can't really be any error there. Well, the tolerance of the components will of course make an error, but apart from that there shouldn't be any. And let me just try to put this in every possible combination of the pins here. Nothing there. It's conducting a little bit, but it's not enough to turn on the green LED, and of course it shouldn't turn on. And here it is shorting out the test resistor, and it's still not coming on. And here I noticed that if you get it just right when you put it in, you can just make the green LED flicker a little bit. But it doesn't stay on. I guess that's because the contact resistance hits a point in between our two comparator values, or comparator voltages. Nope, nothing. And this should be the correct position, and it turns on. There's a little bad contact here, but again, I'm not planning to use this connector. It's just a test. And there's nothing here, and it's shorted out again. So let's put it to the PNP position. And now it shouldn't come on, no matter what we do. And it doesn't. But I do have a PNP transistor here, so let's try that one. Nothing. And here it comes on, and that is the correct pinout. And here we have a nothing. 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 And nothing. Let's try to put it on the NPN position. We shouldn't have any greens. Nope. And I have a BD140 PNP transistor here, and we can try that as well. And we're still in the NPN setting, so we don't expect any matches. I don't actually know if this can make contact. Oh yeah, it shorts it out, so it must do. Nope, nothing there. So let's put it to the PNP position, and now we should have one match.
Nope.
Yes, and we get a green here, but it says 8 in gain, so that is not correct. So the upper value here is a bit off, I'm afraid, so I'll have to correct that. And I was aiming for a gain of 15 to 20 because I knew that there would be some leakage through some of the transistors. So we'll have to fix that. Let's just check. There should be a correct one as well. Yeah, here it is. This is 130 in gain. That sounds like it's correct. Let's hope we don't get any more of those. So it seems to be working just fine, except that this value is too high. So I will try to drop this to a 220k, and we'll see if that solves the problem. And so I changed the resistor to a 220k, and let's try to see if we still have the problem. Oops, that was in the wrong way. Oh yeah, so that was the correct pinout and the LED should light up. It was over here we had the problem, like that, and we still have that little bit of leakage through the transistor, but now the LED does not light up, so that's a good thing. We just have to check how far off our mark that this lower value is now. So I think I'll try a resistor for that instead of a transistor. So I can use a 22K resistor to create a 15 millivolt voltage drop across this resistor here. Let's try that. So that should simulate a gain of 15. If I can get in there, the LED turns on. And yeah, we're getting 15, almost spot on. But that is on. That is kind of my mark to have it at 15. So let's try to take a bit higher value. So if I take a 27K, I don't want it to light up. And I have a 27K here. And it does still light up, so I have to lower the resistance even further. Well, I don't know. I have to check with the lowest gain of common transistors and the highest leakage, because I don't want it to turn on at any leakage. But then it's better that it doesn't turn on when you say if you get a transistor with a gain of only 12. Well, you can still read the gain, but if you have a transistor with high gain and a high leakage, that you don't want it to show you a wrong pinout, because if you don't have the multimeter connected, you cannot see if it's a gain of 200 or just a gain of 12. So I will have to have a little bit of a read about that, but I think it should be at least 15, this one. The transistor I have with the lowest gain is a gain of 40, and that is a rather large one. So, but anyway, I'll check that, and I'll come back with the result when I get it. So I went and searched on DigiKey for the transistors with the absolute lowest gain, but the number that shows up in the list view is actually incorrect, so I had to check a whole bunch of datasheets. And the one with the lowest gain I found has a gain of 18, but that was around 250 milliamps, and the gain is dropping as the current is increasing, so it could actually be more than 18, but I didn't find any with less, so I guess they are not very common. And also I couldn't find anything about leakage or anything like that, so I'll set this around 20, so I'd rather have it not turning on if you put it in correctly and it's a very low gain transistor, and it turns on when you put it in incorrectly if there's some leakage. So I went and changed the resistor and the voltage divider from we started with 270K, and I have already dropped it to 220K, but I ended up using a 120K instead. And now let's check the lowest gain. So I just put a potentiometer in here so we can adjust it. And we're just like simulating a transistor here. Yeah, so it's around 21 or 22, something like that. Yeah, so it's just around 23 millivolts, meaning 23 in gain. So I think that's just fine. So I have also looked up the discharge curve for a 9-watt battery, both alkaline and zinc chloride like this one. And I must admit that I was wrong when I said it would be dead at 7 volts. Well, that is true for higher discharge currents, but at about 20 milliamps or thereabouts, it's more like 6 volts or something. So I have dropped the cutoff voltage for the circuit here down to about 6.5 or thereabout. So let's just check that. and yeah, it's just about 6.6 volts. I still want to have a good margin over the 3.3 volt regulator, because we will need to have the input voltage a few volts above that, so I just chose a resistor that was a standard value. So I mean 6.5 is fine, I can live with that. But I noticed another problem. Before, with the cutout voltage at 7.2 volts, when I turned down the supply we could just see the LED light up at around 3.3 volts, but that has gotten a bit worse now. So now that is, it's not full on, but it is indeed visible, so we have to do something about that. So the easy solution would of course be to put a Zener diode instead of the diode I already have in series with this. And if that is a 3.3 volt Zener, then it will not be able to light up at this voltage at all. And when we get to 6 volts, it will still be able to light up, and we just have to change the resistor to adjust the current a little bit. Or I think we could actually just change this to a blue LED, and I think that will fix the problem as well, because there's a higher voltage drop across a blue LED. So let me just try that. So that seems to have solved the problem, and I will change this diode to a 3.3 volt Zener anyway, and I'll have to see if I need to change the resistor. And it is still working, and now there's absolutely nothing until we get to 6.5 volts. And now it should indeed work with every color LED. There we go. And it is still bright enough, so I don't have to lower the resistance. It is actually very bright at 9 volts. So I am quite happy with this now, and I'll just put it in a case and show the final result. And here's just one last look at it before it goes into the box. So here is the finished product. I just put the labeling on here with a marker pen, so it's not as pretty as it could have been, but that will do. I ended up using a Molex connector for the test port here, because I found that it can take everything from a TO220 to a regular TO92 package here. So that works out pretty good, and it's very easy to make a plug that goes in here if you want to test like a TO3 or something. Well, I am still curious about this transistor that I showed you in the beginning, so let's test it. Well, it turns out that it is a NPN transistor, and it has collector base emitter as the pinout, and it's got a gain of 86. So let's just double check with this old multimeter here. And this is agreeing. It's a little bad contact. That's saying 92, but again I have no idea about the accuracy of this one. And this is saying 85. And you can see this is drifting a little bit, and that is actually me warming up the transistor with my fingers. Oh, now it's cooling down, but if I touch it again, this should rise. So you can see the gain is actually highly affected by the temperature. And typically there is a graph in the datasheet that will tell you the gain versus the junction temperature. So let's just try another one. And I don't know if this is an NPN or a PNP, so I'll just try it out. Oop. Last possible option. So that would be a PNP. It has base collector emitter from this side, and it has a gain of 210. So I hope you liked the video, even though it got a bit long and I had to correct a few mistakes on the way, but if you did like it, please give it a thumbs up and subscribe to my channel. And I will of course put the latest schematic and the board layout and everything on my website, easy-projects.com, so you can find it there. And feel free to leave any comments on what you think about the project and the product. And I will catch you soon. See ya!